Hello guys, my name is Amit. So today we are going to discuss Merkle trees. So Merkle tree is also called the hash tree. So why and what's the use? And basically I'll be discussing this use case that is retrieving the lost or the corrupted data using the Merkle tree in login steps. So basically Merkle tree can be any array tree, that is a parent can have a number of children, but I have taken a use case of binary tree. So Merkle tree actually stores the hash of the data as leaf nodes. Data can be any audio file, video file, or text file, or it can be any character from the dictionary, or it can be anything, right? So here, I have taken the data as something as let's meet at 8 in Tombstone Back Park, and we'll be sending this data from Alice to Bob. And there will be one intruder, that is John, which will change the data, and then we'll see how Merkle tree can retrieve the corrupted data or the lost data and how efficiently as compared to sending whole data back. So this is the data that is let's meet at 8 in Tom Back Park maybe. So these are the hashes which are calculated. So hash of let's is h1, hash of meet is h2, so on for at is h3, uh, h4 is hash of 8, and so on, right? So now, so and so on, that h7 is hash of back, h8 is hash of park. You can see from here. Now uh, we again calculate the hash to construct the binary tree from bottom up. So hash of h1 and h2 is h9, which becomes the parent of h1 and h2. So hash of h1 plus h2, or maybe this might be some other operation, XOR, or maybe some other operation is h9. Then hash of h3, h4 is h10. Hash of h5, h6 is h11. Hash of h8, h7 is h12. And similarly, we'll combine these hashes to get h13 and h14, and hashes of h13 and 14 combined to become the root hash or h15. Now let's suppose Alice want to send the data to Bob. So the data is here. Let's meet at 8 in Tom Back Park. So there will be some encrypted hashed metadata which will store the Merkle root hash. So since this is encrypted and before Alice and Bob send this data, they may have set up a VPN tunnel, maybe set it up using IKE. They have already exchanged the public-private key pair using IKE, and then they are sending this data. So let's say Ellie send that let's meet at 8 in Tom Back Park. John is intruder. This is plain text. It changes 8 to 7, but it cannot change the meta, this one, H15, which is the Merkle root hash because it's encrypted. So now John will send this data. That is, let's meet at 7 in Tom Back Park, and the Merkle root is 15 only. So when this data, this one, is received at Bob, what Bob will do, Bob will calculate hash of the complete data, that is all this, in the similar fashion, which the Merkle root, Merkle tree, he'll construct a Merkle tree from here as done by Alice. So he'll have hashes 45, and he'll decrypt uh, the hash metadata and get the hash as 15. So now hashes mismatch, H45 and H15. So now in the plain old scenario, Bob will say that data is corrupted or data is lost. Please resend the data. So Alice has to send complete data. That is, let's meet at 8 in Tom Back Park. And then he'll check again, and that's fine. But now in this case, these are the levels. That is H45, H43, 14. These are the levels of the tree. So what will happen is Bob will say that send me level 1 hashes. So this is the level 1. So we know that somewhere below this root node we have the corrupted data, but where is the corrupted data we still do not know. But between these two, so we ask send us the level 1 hashes. So correct level 1 hashes are H13 and H14. So Alice will send H13 and 14. So he'll compare and find that H43 is not equal to H13. Sorry, let me edit it and correct it. Sorry for that. So H13 is not equal to H, and H14 is equal to H14. That's fine. Okay. So now, give me a second. Thank you. So now he finds that H43 is not equal to H13. So this Bob comes to know that somewhere below this H43 tree there is some corrupted data. So now he'll ask, send me two hashes at level 2. So we know that if we traverse a binary tree in level order traversal, that is something like 45, then we'll traverse from left to right. There's 43 H14, and then we'll traverse from here. So it's something like zigzag here. Uh, so we'll traverse 45, then we'll traverse in level order traversal. This will be traversal will be H45, 43, 14, 9, 14, H11, and so on, right? So now he'll ask, send me first two nodes of level 2, because we know that the corrupted data is somewhere under this one. So he'll say send first two hashes of level 2. So he'll send H9 and H40. So now again, H9 and H10, which were the correct hashes, right? H9 and H10. So now he'll compare H9 is fine, but he finds that H40 doesn't match H10. So now he says that send me third and fourth hashes of level 3, right? Because we know the some data is corrupted under it. So now he gives back H3 and H4. So with H3 and H4, we got to know that H4 is not equal to H41. Now simply he can ask the data, which is hash of the data from which H41 hash is generated, or maybe H4 hash is generated. So he'll say send the word corresponding to H4. So only 8 is sent. So correct, he'll assemble the correct data. That is something. Let's meet at 8 in Tomback Park. So if we see here, we have, if we consider this all at every word as 1 MB file, so we have 8 MB of data, and so we only sent 1 MB of data to correct the whole uh, our file, or maybe the whole collection of data, and that saves bandwidth, actually, also time. So in this case, the advantage is it saves the bandwidth. If we have a huge file, then complete file need not to be sent. The malformed chunk can be identified and sent. So that's about the Merkel tree or the hash tree. Um, Thank you guys. If you have any questions, just leave in the comment section. Thanks a lot. Have a good day.